video, in the intro, we talked about different ways of representing information, and I think we focused on area models in 3.1.1, but in 3.1.2, we're going to look at tree diagrams. So your teacher challenges you to a spinner game. It's a super exciting game. You spin the two spinners shown at right. The first letter comes from spinner number 1, and the second letter comes from spinner number 2. If the letters can form a 2-word English word, you win. Otherwise, your teacher wins. Test your ideas for the spinner game. So I don't know. Is it worth clicking on this? Let me pause and see if it's worth opening that up. So it's, I guess, marginally okay. So there I spin, I get an A. Here I spin, I get an F. F is not a word, so teacher would win that one. Here I get an A. Here I get an F. Again, a loser. Here I get an I. Here I get an F. If is a winner. So that's how this thing works. So to go back over, it says, are the outcomes for spinner number 2 independent of the outcomes of spinner number 1? Essentially, that means doesn't matter what happens on spinner number 1 as far as what happens on spinner number 2. And I would argue that they are independent. Spinner number 2 has no idea what happens on spinner number 1. So it's completely irrelevant to spinner number 2 what happened on spinner number 1. And again, that makes them independent. It means that that they don't go together, for lack of another word. So are the outcomes? Yes. Spinner 1 has no bearing on spinner 2. All right, so it says make a probability area model of the sample space and then calculate the probability that you will win this game. So I'm going to pause and set this up so you don't have to watch me do it. But it actually doesn't look that bad. So a couple things I want to talk about here are the odds. So you can see I happens 1/2 of the time on spinner number 1. It's half of it. But instead I went for 3/6 instead of saying 1/2, or I could have used 0.5 as a decimal. So there's a lot of different ways I could have written this, but I chose 3/6. Again, it doesn't make it right. It's just a matter of convenience. And the reason why I put 3/6 is if you look over here, you can see that U happens 60 degrees. That's not a percent. 60 degrees out of 360 degrees in a circle, right? So I had a couple of thoughts on what I could do there. What I could have done is I could have just divided 60 divided by 360, and I could use a decimal. So I could have put 0.1666 and 0.5 here, but then, I don't know, it just didn't feel very like a great way to do it. So instead what I chose to do is I chose to just use fractions and simplify them. That's 60 out of 360. Those zeros lop off. 6 goes into 6 once. 6 goes into 36 6. So I just simplified my fraction. Well, the idea is, since I had a 6 on bottom here, I thought it would be easier to keep a 6 on bottom for all of these. Again, I could have made this 1/2, but it's just easier to compare 3 out of 6 to 1 out of 6. It's not as easy to compare 1 out of 2 to 1 out of 6. I think it's just easier to compare 3 out of 6 to 1 out of 6. Again, you don't have to do it that way. So there's multiple ways. Every year this happens. I get kids saying, I did this, I did this, I did this. There's so many different ways that you can do this correctly. This is just what I choose to make it easy for myself. So now obviously if 3/6 are the I, 1/6 is the U, there's only thing left is 2/6, right? Because 3, 4, 5, 6, it has to add up to 6 out of 6. That's the whole. You also could have realized, well, this must be 180 degrees, so 60 plus 120, these are supplementary. And then you could have said 120 over 360 is 1/3, which is also 2 out of 6. So there's a lot of different ways you could have done this. I know I'm spending a lot of time on this, but I want you to understand why I set it up the way I did. All right, so here, obviously that's a 90-degree angle. So that would be 90 over 360. So again, we lop that off. We get 1 out of 4. So if the true is 1 out of 4, I'm sorry, if the t is 1 out of 4, that's not true and false. If the t is 1 out of 4, the f is 3 out of 4. And now again, I have a common denominator. And what I'll do is I'll multiply the tops. 1 times 3 is 3. 4 times 6 is 24. 1 over 24, 2 over 24, 9 over 24, 3 over 24, and 6 out of 24. So this is how likely I am to get an IT or an IF or a UT or a UF or an AT or an AF, right? And you'll notice they are all over 24, even though on this one I wrote a 26. I don't know why. So sorry for that. And the other thing is I should be able to add these all up and they should equal 24. So 3, 4, 5, 6, 15, 18, 24. So 24 out of 24. This is all the different ways that this can happen. And again, you'll notice that the things with the F happen more. Look how much bigger the F is than the T. So 9, 12, 18 of these 24 ways include the F, but only 6 of the 24 ways include the T because the T is less likely. I hope all this makes sense. Again, I know I'm spending a lot of time on this. It's the first time we're doing one of these. I want to make sure we're all on the same page. So now what we're going to do, we have the probability area model of the sample space, and we're going to calculate the probability you'll win this game. Well, let's look at all the winners. IT is a winner. IF is a winner. IT is a word, and IF is a word. UT is a loser. UF is a loser. AT is a winner. AF is a loser. So if I count up the winners, it's not 3 out of 6, right? Because this happens a lot more than this. So don't just say it's 3 winners out of 6. Instead, say it's 3, 4, 5, 14 of 24 are winners. That's how often you're going to win this game, and you'll lose it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of the 24 ways are losers. 14 of the 24 ways are winners. It says, is this game fair? If you played 100 times, who do you think would win more often, you or your teacher? Can you be sure this will happen? So a couple of questions here. Is this game fair? No, it's not fair. Not fair. You'll win more than you lose. Well, you should win more than you lose. You should win more than you lose. And then it says, can you be sure this will happen? You cannot be sure this will happen, that you will win more. Because you might get bad luck. Or, maybe the spinner's broken and it always ends up on you, right? This U, you never win if the first letter is a U. So what if the spinner's broken and it always comes up a U? Then you're always going to lose no matter what happens on spinner number 2. So you just got to be careful with that kind of a thing. There's a lot that goes on with probability. Again, I know I spent a lot of time on this problem, but I did that for a reason. So let me pause and set up the next problem. Player drew a tree diagram at right to model the spinner game problem. So the first one you can get an I, the second one's a U, the third one's an A, and then from there you're going to get a T or F. So it's exactly like what these spinners look like. Sabrina says that can't be right. This diagram makes it look like all the words are equally likely. What is Sabrina talking about? Well, she's correct, right? I happens a lot more than U and A, but it looks like it's just as likely to happen here. F happens a lot more than T, but it looks like it's equally likely. So we're going to have to modify this tree diagram a little bit to make it useful. It says, to make the tree diagram reflect the true probabilities of the game, Sabrina writes numbers on each branch showing the probability that the letter will occur. She writes a 1/3 on the branch for A and a 1/4 on the branch for T. Follow Sabrina's method, copy the tree diagram, and label the probabilities on each. So here's what I'm going to do. First of all, I'm going to use the probability she uses. She's simplifying. So she writes, there's a 1/3 of a chance, which is true. There's a 1/3 of a chance you get an A here. And there's a 1/4 of a chance you get a T here. I should write that there. Okay, so that's 100% correct. But I want to show you why I don't simplify. So you could put a half here. There's a 1/2 a chance you'll get an I. And like we said, there's a 1/6 of a chance you'll get a U. Well, none of this is false. There's a 1 in 4 chance you'll get a T. And there's a 3 in 4 chance you'll get an F. And I know this looks small, so hopefully you're listening as I say. So let's multiply this out. It would be a 1/2 times a 1/4, so there's a 1 in 8 chance you get a T. It's a 1/2 times 3/4, there's a 3 in 8 chance you'll get an IF. So, I'm sorry, a 1 in 8 chance you get an IT, a 3 in 8 chance you get an IF. 1/6 times 1 1/4, there's a 1 in 24 chance you'll get a UT. 1/6 times 3/4, there's a 3 in 24 chance you'll get a UF. So none of this is false. This is all true. But here's what I don't like about this. I don't like to compare 1/8 to 1/24. I like to have that common denominator. So let me zoom in a little bit on this. This is all correct. Again, I'm not saying this is wrong. It's true. All this is true. But I don't like to look at it this way. I prefer to use, like I showed, common denominators. So even though this could be written as 1/2, I'm still going to write it as 3/6 and 1/6 and 2/6. And again, the reason I'm going to do that is when I multiply them out, all the odds will be in a common denominator. So you don't need to do that. That is just my personal preference. Over the years, I just decided when it's possible, I like to work with the common denominator. So there we go. 3 out of 24, 9 out of 24, 1 out of 24. And now I can easily make a direct comparison. And again, I also know if I screwed something up, because these should all add up to 24. So 3, 12, 13, 16, 18, 24. So they do indeed add up to 24. So it says, follow Sabrina's method, copy the tree diagram. Again, I like her method, but I use a common denominator. It says, according to the probability area model that you made in problem 312, what's the probability you'll spin the word at? Well, it ended up being a 2 out of 24 chance I would get at. And you'll notice here I still have a 2 in 24 chance, so, or a 1 in 12 if you simplify it. So it says, now examine the bolded branch of the tree diagram above. How can you use the numbers you have written in the tree diagram to determine the probability of at? Again, you're going to multiply 2/6 by 1/4, and you'll get 2 over 24. Does this method work for the other combinations of letters? Well, if you'll remember, there was a 14 out of 24 chance I win, and there was a 10 out of 24 chance I lose. So let's see if that's still the case here. So it is a winner, if is a winner, and are losers, at is a winner, and af is a loser. So 3, 12, 14 out of 24 ways are winners. 1, 4, 10 out of 24 ways are losers. So yeah, these are the same. So yes, it does match. Same as area model. It says identify all the branches with letter combinations that make words. Use the numbers written at the end of each branch to compute the total probabilities that you spin a word. We already did all that. So does this probability match the probability of the area model? Yes, it does. So again, I already did this one. All right. My handwriting is terrible. I apologize for that. I'm going to pause this video and keep going. Ryan has a pet rat, Romeo, that he boasts is the smartest rat in the country. Sammy overheard Ryan at the county fair claiming that Romeo could learn to run a particular maze and find the cheese at the end. So I don't think Romeo is that smart. Sammy declares, I think the rat just chooses a random path through the maze. So it says Ryan has built a maze with the floor plan shown right. In addition, he has placed some cheese in the airtight container so Romeo cannot smell the cheese in room A. So the cheese is here. It says, suppose that every time Romeo reaches a split in the maze, he is equally likely to choose any of the paths in front of him. That's important because if he always goes right or if he always goes left, none of this will really matter. So this mouse essentially like rolls a die or flips a coin and keeps it even between whether he goes up, down, left, or right, or whatever. So it says, choose a method and calculate the probability that Romeo will end up in each room. In a sentence or two, explain why you chose the method you did. So here's what I'm going to do. I'm going to figure out the odds. And now this gets a little bit tricky because just like in the previous example, I said I'd like to have a common denominator if I can. Well, in this one, it's going to be trickier to have a common denominator because the first one, I have a 1 in 3 chance of going to the top, a 1 in 3 chance of going to the middle, and a 1 in 3 chance of going to the bottom. But from there, here I have a 1 in 2 chance of going up and a 1 in 2 chance of going down, whereas this one I just go straight into A. There's no more choices. And on this one I have a 1 in 3 chance of going here, a 1 in 3 chance in the middle, and a 1 in 3 chance on the bottom. So the multiplying of this gets a little bit confusing, but ultimately what we'll do is we will say, all right, if he goes down and down again, there's a 1 in 6 chance of getting in the, actually I'll just put it over here. So there's a 1 in 6 chance of him going this way. Here, there's a 1/3 times a half, so there's a 1 in 6 chance of him coming in here. And I'll put there's an A, this is a B, just so we keep track of what room he's in. If he goes straight, there's a 1 in 3 chance he just goes straight into that A. And you'll notice I have these not the same denominators, so it's going to be a little bit trickier to compare. If I end up in this door, it's a 1/3 times a 1/3, so there's a 1 in 9 chance that he ends up in this A right here. And then here, it's a 1/3 and a 1/3. There's a 1 in 9 chance he ends up in this B, and a 1 in 9 chance he ends up in this B. So that's going to be our breakdown. Now, if we wanted to, we can go ahead and we could get a common denominator from here. Like what number do 9, 3, and 6 all go into? It looks like the smallest one is 18. So we could rewrite these to all be out of 18 to make it a fair comparison if we wanted to. I would say let's go ahead and see what the questions are and see if it makes sense to do that. So it says, if the rat moves through the maze randomly out of 100 attempts, how many times would you expect Romeo to end up in room A? So yeah, I think common denominators wouldn't be the worst. So 1/9 is the same as 2 out of 18. So these three are all going to be 2 out of 18. So I'll go ahead and write that. 2 out of 18, 2 out of 18, 2 out of 18. This is going to be, 6 out of 18, and a 3 out of 18, and a 3 out of 18. So 6, 3, and 3. So just have those common denominators. And again, if I add all these up, it should add up to 18, 2, 4, 6, 12, 15, 18. So these are the 18 different ways this rat can get through the maze. And the question is, how many times would he end up in room A? Well, he would end up in room A 2, 8, 11 out of 18 times. So how many is that out of 100? So actually, it would probably make more sense if I did this. If he goes in 11 out of 18 times, how many times would he do it out of 100? There's a lot of different ways we can do this. Obviously, you can just divide and get a decimal, but I'm going to set this up as 18x equals 1100. I'll divide by 18, and I will get my answer as 1100 divided by 18. So he will 61 times. 61.1 times out of 100. So he's more likely to end up in room A and get that cheese. So it says after 100 attempts, Romeo found the cheese 66 times. See how smart Romeo is? Ryan asks. He clearly learned something and got better as he went along. Sammy isn't so sure. So he should have found it 61 times. He found it 66 times. Do you think Romeo learned and improved his ability to return to the same room over time? Or could he have just been moving randomly? Discuss the question with your team and then write an argument that would convince Ryan or Sammy. Well, I don't know if anything's going to be convincing. He did find the cheese more than he should have, but it could have just been luck, right? So let's say I flip a coin 10 times. I'm not necessarily, I might get 5 heads and 5 tails, but I might get 7 heads and 3 tails, or I might get 9 heads and 1 tail. It's unlikely, but maybe I will, right? So the fact that the mouse found the cheese more than he was supposed to, it wasn't by much, right? It's not like he found it 100 times out of 100. So I would say I think the mouse got lucky would be my guess. And if he did it again, I'm not sure he would find the cheese more often than not. So it says, always skeptical, Sammy says, if Romeo really can learn, he ought to be able to figure out how to run this new maze I've designed. Examine Sammy's maze at right. To give Romeo the best chance of finding the cheese in each room, in which room should the cheese be placed? Should it be in room A, B, or C? It says choose a method. And so let's go ahead and figure this out here. So first of all, there's a 1 in 2 chance he goes to the top. There's a 1 in 2 chance he goes to the bottom. If he goes to the top, there's a 1 in 3 chance he ends up here, a 1 in 3 chance he ends up here, and a 1 in 3 chance he ends up here. If he goes to the bottom, this is like two separate decisions. There's a 1 in 2 chance he goes up from here, and a 1 in 2 chance he goes down from here. A lot of time kids over the years have looked at this maze and they've kind of looked at it as like these all happen at the same time. It's not true. So there's a 1 in 2 chance he goes there, and then he's got another 1 in 2 chance of going here, or 1 in 2 chance of going here. However, if he goes to the bottom, he just goes straight in. So there's a lot going on here. So first of all, to end up in room A, he could go a half times a third, so it's 1/6, or he could go a half times a third, so it's 1/6. So that's if he gets in room A. For room B, it's a half times a third for this room B. But to get into this room B, it's a half times a half times a half. Because he's got to make 3 decisions, right? So there's a 1 in 8 chance. There's a 1.5 chance he goes here, a 1.5 chance he goes here, and then a 1/2 chance he goes here. So those are the ways he can get into B. What about C? To get into C, it's 1/2, 1/2, 1/2, which is of course an eighth. Again, 1 times 1 times 1. 2 times 2 is 4 times 2 is 8. Or he could just have a 1 in 2 chance and a 1 in 2 chance. So there's a 1 in 4 chance he ends up in this bottom C. So these are the odds he gets in the room. And now some kids are going to say, well, look, there's 2 doors, there's 2 doors, there's 2 doors. That's not how it works. We have to figure these odds out. So now what would be the best thing to do is let's make a comparison between 6, 8, and 4. So what number do 6, 8, and 4 go into? Right? Well, it looks like they would all go into 24. So I can make this 4 out of 24. Can make this 4 out of 24. I can make this 4 out of 24. This would be 3 out of 24. This would be 3 out of 24. And this would be 6 out of 24. Hopefully we're okay with our fractions. So again, it should add up to 24. So 4, 8, 12, 15, 18, 24. It does. It looks like there's an 8 in 24 chance I'm going to end up in room A. It looks like there's a 7 in 24 chance I'm going to end up in room B. And it looks like there's a 9 in 24 chance I'm going to end up in room C. So it says to which room should the cheese be placed? It should be placed in room C. That's the one that makes them the most likely. It says if the cheese is in room C and Romeo finds the cheese 6 out of every 10 times. Well, let's think about this. He should be finding it 9 out of 24. He should be finding it 9 out of 24, which is 37% of the time, but he's actually finding it 6 out of 10 times. Well, that's significantly different. So yeah, if he's finding it that much more, if he finds it 60% of the time instead of 37% of the time, I would say he seems to be learning because it's such a higher percentage. All right, it says make an entry in your learning log, so I will leave that for you, and I will close this video. Sorry it was such a long one.